Welcome back. And if you are in Unit 3, some of this content around reactions is going to be a little bit of a refresher for you. If you're in Unit 1, it will be fairly new content for you and it might seem a little bit confusing. So you might need to just take a step back for Unit 1 and explore the idea of reactions a little bit more finitely and broken down. Okay, so our prior knowledge that we learned about in Unit 1 was all about vertical reactions, and we need to ask ourselves what is happening at the supports. So we have a typical sort of situation where we'd be considering reactions like a bridge, and we've got our supports, and we need to be thinking, okay, we've got our load, our mass on top, and the supports here, and what's actually occurring. Okay, and I want you to really consider that idea of the word reactions. So with our reactions, we generally talk about typical supports when we're drawing our free body diagrams. Do you remember what those are? So we have our pin or fixed joint. And remember, in theory, a pin or fixed joint allows the system to move like this, but it doesn't allow the system to move like this. Okay. We also have a roller joint. Now, a roller joint is really important. It does allow the system to move like this, and you need to sort of gain an understanding of why that's important. Wonder if you can remember that. So the sorts of reasons why a roller joint is important is to allow for things like the natural vibrations as cars drive over the bridge. It might be to do with the expansion and contraction of steel and concrete as the system heats up throughout the day. That's what a roller joint looks like. So you can literally see that idea of the system rolling. Okay, so on to our reactions. Here's an example where we've got two students and they are supporting a beam with a mass in the middle. Now that mass is 15 kilograms. So using our, just basic mathematical knowledge, we should be able to have an understanding that at both end of the beam, the students are both feeling a support, a mass in their hands, equal because the mass is in the middle, and that should be equal for both students. Now, it's easy for us to work here and think, okay, well, we've got 15 kilograms, there's two students, so therefore we're going to have 7.5 kilograms each, okay? That should be fairly basic for you to understand. Now, if we were to draw a free body diagram for that, it might look something like this, okay? And that's where we need to start our thinking. Okay, so we've got Tom, he is going to be our reaction left, and we've got Jake, our reaction right. Now, the beam that they're holding is 1.6 meters, and at the moment it's 0.8 meters from the end where the mass is. That's smack bang in the middle. Now, I said before, I want you to think about that word reaction and what that really means. So if we've got a pushing force coming from one side and it's pushing against something, if the system is going to be in equilibrium, if there needs to be a reactive force acting against in the other way. So think about Isaac Newton's third law. For every action, there must be an equal and opposite reaction. If we've got a pushing force occurring here, if there is no reactive force occurring back in the opposite direction, then that pushing force is going to continue on in that direction, okay? And so if we know that the system has to be in equilibrium, then we know that there needs to be an equal and opposite reaction occurring back in the other opposite direction. Okay, back to this example. We've got our system. Now, we want to talk in terms of newtons, not kilograms. So using our formula of force equals mass times acceleration, we can determine that we've actually got a load of 147 newtons, and that is pushing down. Okay, we need to assume our directions. So because in this case, I'm going to work from the left-hand side. So I'm going to say that a clockwise movement is a negative value, and therefore an anti-clockwise or a counterclockwise movement is going to be a positive value. All right. So when we explored this in Unit 1, my students, I get students to break down the equation into pieces. Okay. Now in this case, we're only really using one force, but there are two things occurring. So we've got, we're taking the moments from the left-hand side. Okay, so we've got sum of moments left equals our force coming down is 147 newtons multiplied by our perpendicular distance is 0.8. Now think about what we're doing for the second part of the equation. I've then got a positive value, reaction right, multiplied by the total distance of 1.6. Okay, so you should be able to have a think about this. We've got a load pushing down 147 in the middle, and then at the right-hand side, because we've got a reaction force, we're going to say that it's a positive reaction pushing up into the system in the opposite direction. And that's then multiplied by the total distance of the system, 1.6 meters. Now, the trouble is we can't punch that into our calculator just like that. We can't type in reaction right. So what we need to do is we need to move the reaction right to the other side of the equation, okay? And when we do that, it becomes a negative value. Because we've switched it to the other side of the equation, it then becomes negative reaction right equals negative 147 times 0.8. And because we've switched that reaction right around, our 1.6 isn't a multiplier anymore, we now divide. So it's negative 147 times 0.8 over 1.6. And that's something that we can punch into our calculator. When we do that, we end up with negative 73.5 newtons. Now, don't get fooled by the negatives. We've got two negatives here. It says negative reaction right equals negative 73.5 newtons. So of course, those two negatives cancel each other out, which means our reaction right is actually 73.5, and it's pointing up in the upwards direction. So remember, this one took me a little bit of time when I was learning this stuff to get my head around it. When we're trying to find the reaction right, we take the moments about the left side. When we're trying to work out the reaction left, we take the moments about the right side. Now we can go and prove this. We could go and do exactly the same thing as what we've just done, but taking the moments about the right side. Or if we know that there needs to be a balanced system to make it in equilibrium, then we know that if there is 147 pushing down, there needs to be 147 also pushing up. So I framed it like this. Sum of forces vertical equals 0. That means it's in equilibrium. Equals negative 147 plus 73.5 plus reaction right. And when we flip that all around, we prove that the reaction left is also 73.5 newtons, also pushing up. Now, what happens in this situation when we shift the center of the mass? Okay, maybe we've got this situation where our two guys, Tom and Jake, maybe Jake's stronger than Tom, and he is required to lift more mass. Okay, so remember, we need to draw our free body diagram to get us started, and it's going to look like that this time. You can see that the mass changed its position. Those same rules apply. So we've got a clockwise direction for a negative value and a positive value for an anti-clockwise direction. And this time we've said that it's 0.3 of a meter away from the right-hand side of the system. So we go and input our numbers again. This time it's negative 147 times 1.3. Okay, so it's 1.6 minus 1.3, 0.3, I'm sorry. Plus reaction right times 1.6 again. And that gives us our value of reaction right, 119.5, pointing up. So how much is Jake actually supporting of the 15 kilograms? We then go through and find out what Tom is holding. So we can substitute in exactly the same way as we just did before. We've now got negative 147 plus 119.5 plus reaction left, which is Tom, equals negative reaction left equals negative 147 plus 119 equals negative 27.5. The negatives cancel each other out, so therefore Tom is supporting 27.5 newtons of mass. Now, that might not be all that helpful for us if we actually need to know what our result is in kilograms. So again, we can use our formula for force equals mass times acceleration to determine that Jake is supporting 12.2 kilograms of force and Tom is only supporting 2.8 kilograms of force. Hope that helps refresh your memory around reactions. We'll be moving on and introducing horizontal reactions